In this video, we discuss section 2.3 bases and dimensions. That is section 2.3 bases and dimensions. So first we define linearly dependent set. Let V be a vector space. Over F. The corresponding field is F. And S be a subset. A subset S of V is said to be linearly dependent. Or simply we can say this is a dependent set if there exists alpha 1, alpha 2, etc. alpha n belongs to S and scalars say C1, C2, etc. Cn, these scalars in F not all zeros, not all of which are 0, such that the linear combination C1 alpha 1 plus etc. Cn alpha n equal to 0. Okay, so this if this set S has this property that you can choose a certain number of elements from S and scalars from F such that the linear combination is 0 with the property that the Ci's are not all 0, then we can say that this set S is linearly dependent. Okay, a set is not linearly dependent, then it is called linearly independent set. Okay, so if S is not dependent, then S is called a subset of V. S is called, obviously this is this S is a non-empty set. It's called linearly independent set. So this is the definition of linearly independent set. Now we can see some remarks on these linearly independent sets. The first one is any set which contains linearly dependent set is linearly dependent. Okay, so that is if S is a subset of V and S contains a linearly dependent set. Okay, then S is linearly dependent. That means any subset of which contains a linearly dependent set is again linearly dependent. Okay, that means any superset of linearly dependent set is linearly dependent. Next remark is any subset of linearly independent set is a linearly independent set. Okay, so if S is linearly independent, every subset, say subset S1 of S is linearly independent. Okay, subset of linearly independent set is linearly independent and superset of linearly dependent set is linearly dependent. The third remark is if a set contains 0 is an element of S, then S is linearly dependent. Okay, if S is a non-empty subset of V containing 0, then you can easily write that 1 times 0 is equal to 0. Okay, as this 0 is an element of S and 1 is an element of F. So any set containing 0 is linearly dependent. The fourth one is a condition for testing the linear independence. That means if you have C1 alpha 1 plus etc. Cn alpha n equal to 0 implies each Ci equal to 0, I equal to 1, 2, etc. and then this is the characterization of linearly independence. Okay, so if this holds, we can say that uh, elements alpha 1, alpha 2, etc. alpha n are linearly independent. So in order to verify that a set of vectors is linearly independent, we have to verify this one. C1 alpha 1 plus C2 alpha 2 plus etc. Cn alpha n equal to 0 implies each C is equal to 0. Now this will enable us to define a basis of a vector space. Let V be a vector space, and a basis for V is a linearly independent set of vectors in V which spans the whole vector space V. The space V is finite dimensional if it has a finite basis. Okay, this is the definition of basis and the dimension of V. The definition of basis is a set that should be linearly independent and that should span the whole space V. And if V has a finite basis, then we can say that V is finite dimensional vector space. Now we can see some examples for basis. If we consider R2, R2 is nothing but R cross R. That is a set of all ordered pairs xy such that x comma y are elements of R. This is a vector space. If we consider the set 1 0 and 1 1 set of ordered pairs, obviously this is set B. These are elements of R2, hence it is a subset of R2. So these elements have this property. When you consider C1 times 1 0 plus C2 times 1 1 equal to 0 0 implies from the first component we can get C1 plus C2 equal to 0, and from the second component you can get C2 equal to 0. These two equations together imply that C1 is 0 and C2 is 0. This shows that these two elements are linearly independent. Okay. Now, if you choose any x comma y, that can be written as some a times 1 0 and b times 1 1. Okay. So you can easily find out this a and b in terms of x comma y. Okay, so if we solve a plus b is equal to x, and from second we can get c b is equal to y. So these two equations together imply that a plus y is equal to x and b equal to y. That implies a is equal to x minus y and b is equal to y. Okay, so this shows that any x comma y equal to this a times a means this x minus y times 1 0 plus b times b is y, then y times 1 1. Okay, this shows that any x comma y can be written as a linear combination of 1 0 and 1 1. Now the set 1 0 0 1 0 1 1 form a basis for R2. Okay, so this is an example for basis. For the next example, we consider a system of linear equation x1 plus x2 plus x3 equal to 0. Then x1 minus x2 plus x3 equal to 0. And the last equation is x1 plus x3 equal to 0. Consider this system of equation. We know that the system of linear equation is homogeneous. Therefore, the solution space, if we consider the system as A in the form Ax equal to 0, that is 1 1 1 1 minus 1 1 and 1 0 1 times x1 x2 x3 equal to the vector 0 or the matrix 0. So this is a homogeneous system of linear equations. Okay, we have seen that the homogeneous system of linear equation has a solution space. What are the solutions of this? Solution space is a vector space, obviously. So this solution space is set up for all x1, x2, x3 such that in this case I choose this is from R3 by 1 such that Ax equal to 0. This is the assumption that this system can be considered as a system of linear equation on R. That means the entries, the coefficients of the system, these equations come from the set of real numbers. So when you consider the system of the solution space of the system of linear equation 1, now we know that this is a vector space. Which the next intention is to find out the basis for the solution space. That is our idea. So first we need to explicitly write the solution space. So first next our intention is to find out the solutions. In order to find the solution, you consider the rank of A. This A can be equivalent to, or we can apply row transformations. When you apply the row transformation by adding the first row to the second row, you can get 2 0 2 then 1 0 1. From this you can say that R2 second row is same as, or second row is obtained by 2 times R3. So this shows that this is again equivalent to the matrix 1 1 1. By dividing throughout by 2, you can write it as 1 0 1, and you can subtract the row R3 row R2 from row R3, so you can write it as 0. So this is the equivalent form. Now the system reduces to this Ax equal to Ax equal to 0 reduces to the matrix 1 1 1 1 0 1 0 0 0 x1 x2 x3 equal to 0 0 0. From this you can write this is our x2. The first equation is x1 plus x2 plus x3 equal to 0. From the second equation you can write x1 plus x2 equal to 0, x1 plus x3 equal to 0. Then we have rank of A is 2 and number of unknown is 3. So this is number of unknowns and rank is R. Then you can write it as 3 minus 2, that is equal to 1. So this shows that in order to solve the system of linear equation, we need to put one unknown as a constant. So without loss of generality, let me put x3 is equal to some arbitrary constant k. Then from the second equation, x1 plus x3 equal to 0, you can write it as x1 is equal to minus k. Okay, using x1 and x3, you can get the value of x2. Okay, from the first equation, x2 is minus of x1 plus x2, but x1 plus x2 is 0. Sorry, minus of x1 plus x3. Here x1 plus x3 is 0, so you can write it as x2 is 0. So this shows that the solution space contains the vectors of the form k minus k 0 k. This is the uh, solution space of the linear system of equation x equal to 0. So next we write the solution space. The solution space of the system, solution space of the system is set for minus k 0 k such that k is an arbitrary constant from R. So this is our solution space. Okay. Now you define B as minus 1, 0, 1. Okay. If you write this B as this set, you can say that any x belongs to the solution space. We can write x equal to some k times an arbitrary constant times minus 1, 0, 1. And obviously, whenever c times minus 1, 0, 1 equal to 0, 0, 0 implies c equal to 0. This shows that B satisfies the condition of the conditions of the definition of basis. So this B is the basis for solution space of the linear the system of linear equation. Okay, so this can be considered as another example for the basis. If you consider this linear system of linear equation, you have seen that the number of unknowns is 3 and the rank is 2. If number of unknown is n and the rank is r, then you can say that n minus r variables or unknowns can be chosen as arbitrary constants. So in the general case, you can say that n minus r will be the number of elements of the basis of that solution space. Okay, this is one of the important examples mentioned in the textbook. So this completes the basic idea of definition and basic idea of basis.